welcome to another Learn Electronics Repair video, and this is a part 2 again, so I'll link the part 1. We have here a GTX1070, and this is a graphics card which I looked at in November and traced the fault and basically put it on one side waiting for parts. So this is one of 13 graphics cards I bought from eBay in the UK, spares or repair. And this actually came in a batch of 10 out of those 13, which came from one seller. And that batch of 10 cost me £100 plus the postage, £109.50. So, in the case of this one, basically, and do look at the first video so you can see this, we traced the problem to this chip here. This is the VRM controller for the two phases here, which produce the power for the RAM. So this has no VRAM. And the problem turned out that this has been worked before. Someone's looked at this before and there was a solder bridge on this chip. So I cleaned the solder bridge up and I tried it, but it still just wouldn't generate any VRAM. So I then used a part I salvaged from another GTX1070, a gigabyte board I believe it was, which was the same chip as far as I could tell, and I fitted that chip, and then it did power up for an instance and shut the PC down twice. I tried it, and basically one of these two dual MOSFETs had gone short, the top high side. So basically these two MOSFETs, each one is a dual MOSFET, not a single one, and each one powers one of these phases, and it was one of the high sides that went short. So at that point, I put it on one side and ordered some parts, and the parts are here. So let's see now if we can fix it. So these are the two dual MOSFETs that I've now removed. 4901NF is the part number. And each one effectively has two MOSFETs, as I mentioned before. So there's two gates, and there's the drains and sources, and the drain of one and the source of the other are connected together on this larger pad, and that's the junction that goes to the coil. So they're designed specifically for VRM, for coil drivers in buck regulators. Okay. Now, originally the MOSFETs were okay, as far as I know. I'm sure they were okay initially, and with the original driver, that was one that had the solder bridge on, and it wasn't working. So obviously I took the solder bridge off and powered up again. It was still generating no power. I then found another chip on a donor board, another 780, and it's the same chip, so I fitted the chip. At this point there, when I powered it up, this is when the high side of this MOSFET pair in this one device went short. Now, in my opinion, either of two things has happened here. Firstly, this could be a faulty part. I mean, it came off another board which I'm pretty sure had VRAM, but I could be wrong about that. It had a faulty GPU, but I might have made a mistake and this could be faulty. The second option is that the soldering, when I soldered this little QFN, I haven't got all the pins soldered down properly, so one of the gate drivers is open circuit, and when I switched on, the high side gate floated up and it went short. I explained this on the previous video, if you watch that one, how that happens, the mechanism. So that's another possibility, but for sure there's no point just sticking a new MOSFET in and plugging it in. So I think the first thing we'll have a look at this is to see whether the four gates have the same resistance to ground connected to this chip. I mean, I don't know whether they should, but let's have a look. If they do have the same resistance to ground, we might be able to say, okay, well, look, they're all about the same, so that probably isn't one of those being open circuit. Okay, so I'll get the meter where you can see it, and let's measure some resistances. Okay, so I have the meter on resistance mode. This is the pin out of the device, basically. That's the device, the dual MOSFET, yeah, in one package. So we can see that by this narrow pad, this is gate 1 and this is gate 2, okay? So on ours, that would refer to these two being the two gates. And then the other one's upside down, effectively, so it's those two are the two gates. So I'll measure to ground. I'll just get a good ground point. Now let's have a look. So we have, this is one of the gates. Oh, do I have it back to front? Hold on, that's reading short. This is one of the gates. I have it upside down. That must have been a bottom diagram, and this is from the top side, yeah. So that's a gate, and that's open. And this should be the other gate. And that also reads open. So I'm assuming on this one, it's this side of them. That reads open. So, in fact, they actually all read open. Did they read anything on diode mode? Yeah, we're on diode mode. So, do we see any reading on diode mode? So, open. 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 Okay, so they all read open circuit on diode mode and resistance mode. Now, I don't know what this should read, but obviously I have some replacement ones here of the chip itself. So if we just go down by this chip first, and we can just figure out which pin are the actual gates, and then from there I can measure it around this chip again, just to be sure in case there's some, something broken in between. If it comes through maybe some resistors, maybe. And if I'm seeing the open circuits down here, then I have a new chip, and if we flip the chip upside down, we should be able to measure the resistances on the chip itself and see if they're the same. So this is the little diagram I've made of the actual board I'll show you. So effectively, that's this chip here. So I've used a data sheet to see which pin is which gate driver, enable, VCC, and so on, and worked out just by measuring the resistance from the pins to these various little test points around here where it goes to, and that makes it easy to measure the resistance from there. So we can see we've got enable. This is upper gate 1, lower gate 1. This is PVCC. This is the 12 volt power. Okay. This is lower gate 2, upper gate 2, and this is VCC. This is the power to the chip itself, and that is I think it's 5 volts on this one, if I remember correctly. So we know which pin goes to which pad. So I'll get the microscope and let's have a look, and then we can check some resistances. And what I'm particularly interested to know was on the upper and lower gate 1 and the upper and lower gate 2. Did they read, open circuit to ground, which I'm reading on the actual place where the MOSFETs fit themselves. So this is the chip itself, and just referring to that diagram that I made, the upper gate 1 is on this pad here, and what's that reading? Open circuit, the same as I read actually on the FET itself. And this is lower gate 1 on this. Is it this pad? No. Well, yes, it's this pad, this side of this resistor. So I think I was just touching the pin next to it. Okay, so that's reading open circuit again. And then the lower gate 2 is this one, and it reads open circuit. And then upper gate 2 is this one, and again it reads open circuit. So that's reading the same that I was getting when I actually checked on the device itself. Again, we can just go into diode mode and let's have a quick look, but I'm sure it'll read the same. Okay. So we're on diode mode, and we'll just do them quickly again. So upper gate 1. And you can see, by the way, each one does go through a resistor. The resistors are next to the pads mainly. Upper gate 1, upper gate 2, lower gate 1, and lower gate 2. Okay, so that's reading the same that I read at the MOSFET, basically. I'm interested, actually, to see if this chip has any power now as well. I mean, previously it did have power. So let's just check that we've got enable, VCC, and PVCC. Now, because the MOSFETs are removed and each one has a high side and low side in a pair, it's actually safe to power this up, because nothing can get down to these coils. The MOSFETs are not there. Both of them are not there. So there's actually is safe to power that up. So let's have a look to see if our chip actually has any power and has an enable signal. So we just power the thing on. Okay, we powered on. So enable is actually on this little wire here. Just give me one moment, I'll just get the meter probe onto it. There. And it has 6 volts on that, so the chip's enabled. The VCC is actually on this one here, from the little diagram I made again here. 8 volts. The higher than I thought, it has power. And the other one, the PVCC, is on a little via 12 volts. Okay, so that chip has definitely got power enabled, but the voltage seemed a little bit high, especially on the VCC. I'm a bit surprised why that's reading 7 volts. Let's just have a look to see where that actually comes from if we can, out of interest. So I'll just power it up again. Let's have a look. That's on this resistor here, on this point here. 8 volts. I know it's possible for some GTX cards to have an 8 volt, 7 or 8 volt supply, but let me just actually figure out where that comes from, out of interest. Okay guys, I've sorted out that mystery why we've now got 8 volts on the VCC. I can show you. It's because this power to this chip doesn't come where I thought it came from. Let's just go over to the data sheet for this thing, yeah, the 8811A. So you can see that we have PVCC. This says it's the power supply voltage input, yeah. So that is the actual supply voltage input, and that's the 12 volts. VCC, which is where I had the 5, but now I have 8, or 7.9, is low dropout regulator output. So this actually is an output coming back from the chip. It generates this voltage itself using a voltage regulator from PVCC. And if we go down here, you can actually see it. So this is the power coming in, yeah? An internal regulator, specifically as internal regulator, generates that, and that's where we got 8. And that definitely really confirms to me this chip isn't soldered down properly. Yeah, there's probably no ground on it, and that's why we're seeing some strange voltages here. So let's go back to the board and let's look further. I've removed the chip again, and I think we can clearly see now that this didn't solder properly. So basically, the chip is the right way up, but effectively it's flicked over. So this was pin 1 here, yeah, and I flicked it over horizontally. And you can see, I think if you look at it, that this row down here was effectively here, and that was soldered. You can see that. This side was soldered, but this pin wasn't soldered, which goes there. Okay. And then it looks like only really 2 of these actually soldered, and the other 2 just didn't solder to the chip. And it looks like this side probably just didn't solder at all. So that's bad soldering. That's me. I mean, that was my attempt at fitting this chip. I'm not sure if I just actually made a little solder bridge there. Actually, that's how we go to it on there. Just zoom down on that as well to see what we have. Yeah, it looks like I also have a solder bridge, but that might have happened when I actually removed the chip. Yeah, that might be when we removed the chip there, so we can maybe say that wasn't there. So I'm going to solder another chip, but the problem with QFNs, and I hate fitting QFNs, but I hate replacing the damn things, is that it's almost impossible to tell whether you've got a good soldered joint or not. So I'm going to try something a little bit different. I'm going to start from pin 1 and work around the 24 pins, and I'm going to measure the resistance of each one to ground. So I'm going to go all in turn and measure the resistance to ground from each one, and I'll do it in resistance mode, and I'll redo it in diode test mode. I'm then going to take the replacement chip. I won't use this one, I'll use another one. This might well be okay. I'll take a replacement chip and I'm going to work my way around it. And again, I'm going to measure the resistance from each pin to ground, which is the center pad of it here, yeah? And the idea is that when I fit the chip, if I measure from ground to here, I should see whatever reading this chip shows me to ground here, yeah? Admittedly, if the reading I see here is lower than the resistance I see here, or this is like, you know, open and this reads something I probably won't see on that pin. But hopefully this way I should be able to determine if at least most of the pins, and maybe even all of them, have actually soldered. So I'll just show you on one and then I'll get on and do it. So I have the meter on resistance mode. So the idea is, I mean, I have explained to I'm shooting pretty well, is to start on the chip. So we can go from the ground, which is the center, and we can just check the resistance from each of these pins. See, that one read something that went to over limit. Yeah, that one doesn't read anything. So I'm going to go around these various pins and take a reading. And I'm going to do the same thing in diode test mode. Okay, so we'll go in diode test mode. Again, I'll go on the ground and then we'll do the same thing again just to see whether we see any readings, yeah? And I'll make a note of them all 24. And then we'll do the same with the chip. So in the middle of the chip, ground, and then we can quite literally just go around here and see if we see anything. I mean, if we don't, maybe this won't work. I've not tried this technique before. It's just an idea that maybe we can use this method. Back onto ohms range. Maybe we can use this method to determine if the chip is actually soldered. So, did we read anything? Yeah, see, that one reads something. Some of them are reading something. Okay, so I'll get a piece of paper and I'll go around and I'll let you know what I find. Okay, I've taken all those readings. We can have a look at them after I put the chip on and see if it'll actually help us any. So this is the chip. So I've managed to get a little bit of solder, leaded solder on each pin and on the tab. And I'm hoping that that will actually get it to solder down properly this time. I'll do a similar thing on the board as well. So I'll just put the chip on one side. Let's have a look at this board. So this was what's tidied up a little bit. It's a little bit messy. I've noticed one pad is slightly loose as well. I think this is because this has been, you know, taken off and on basically. And it looks like somebody had reworked it before me. That's why there was a solder pitch to start off with. So we'll just see if we can just get an even little bit of leaded solder on this as well. I might have to use a bit of solder braid. I'll just look down the microscope because that helps me a lot when I'm trying to do this sort of thing. So let's just have a quick look. So we'll just get like an even spread of solder onto it. No shorts. I think I have a shorts here. I think I have a loose pad or something. I need to have a look at that. And this bit here as well. Now let's just get the bit of flux off that. Let's actually have a look to see what's going on. You can see that's not quite ready yet, so I've got like a little bump on that which I need to get rid of. There's a blob on this one and not much of that. I'll just get a solder braid. These two sides look pretty reasonable to me. That side and that side. It's just this area. So let's get a bit of solder braid and a little bit more flux. And so if you can just properly clean this area up and I can actually see what's going on. Or what isn't going on. So a bit of solder braid, a bit of flux on it. I've put a bit of flux on the braid itself. Often a good move. I'll look down the microscope again. Let's see if I can just clean this area up. So let's put a bit of braid. Okay, that's that little blob there. That's cleaner. That's cleaner. That's clean. Okay, let's have a look now. Let's get the flux off that and let's have a look to see if that's looking better. Okay, that looks clean now. I might have to get a bit of solder on it. So it looks like I've got something here. This. I'm not sure what that is. Let's see if I take it off and let's see if that's actually conductive. And there's that little strand of wire or something that's under here. Oh, I bet. Oh no, I know exactly what this will be. That'll be a bit of solder braid. Yeah, a little bit of copper out the solder braid. I don't need to check that was conductive because obviously that is conductive. So, okay. First time I think that's ever particularly happened to me. Okay, I'll now try and get a little bit of solder onto this again, onto the pads. Or maybe, actually, I mean, there's some solder on the chip itself. This is the problem I find with QFNs, is getting to actually sit straight. Let's have a look. So there's our chip, and that's a little bit of solder on the pads. It's whether or not there's enough to get it to stick down to this. Yeah, I'll see if I just get a little bit more solder onto that, and see if I can just, you know, so I'm happy there's going to be enough to make its joint. So I'm going to try and do this. I've got a bit of solder braid. I'm going to try and flood the end of the solder braid with solder, basically. Under here. So I'm just going to try and get the end of this bit of braid full of solder, and hopefully I can then sort of kind of use that to press against the pads, and it'll hopefully, you know, this is the theory, so let's try it. It'll then release solder onto the actual chip. That's the idea. To get the end of this so it's effectively. Oh, sorry, this is probably not. It's probably not staying in shot to do it. I'm trying to do it to show you, but needs more. Let me just do it and I'll show you. So I'm just going to try and flood the end of this bit of braid with some solder. Okay, I've managed to do it as I can show you now. So you can see I've just effectively filled the braid with solder. What I'm going to try and do now is just push this against all the pads. I'm hoping that what will happen is it will effectively leave, you know, a reasonable amount of solder on each pad. That's the idea. Just gently get it hot and put it over the pads. Okay, let's see if that had the desired effect. Okay, I mean, I think that seems to have had the desired effect. There's a little bit of solder on. I mean, there's a little bit more on some pads than others, but I'm hoping that because there's a bit of solder on the chip, this will kind of like pull down when I put it into place. So let's have a look. I've got the chip, and let's just see if this actually wants to sit here fairly flat. That's the next problem. Is it going to sit here flat? So we'll just flick it over. The dot signifies pin 1, and there's a little arrow here which is signifying pin 1. So the chip fits there. Stuck to my tweezers, of course. Okay, just getting into position, yeah. So the chip fits there, and it's sitting reasonably flat against that board. I mean, I think it's slightly raised in one or two places. But what I'm going to do is with this now, is I think if I put the heat in from the top of this, it's just going to blow the chip away. So what I'm going to try and do is use my preheater from underneath and heat this area of this board. And hopefully I'll see that kind of like settle down and pull into place. And hopefully that will actually solder it correctly. Let's give it a go. So I've got a thermocouple taped here. In fact, you can probably just see that's the end of the thermocouple, so that's near to the chip. I've got the temperature meter here. That's the ambience in my workshop at the moment. Bear in mind it's mid-January, so it's winter, but the aircon is off, in fairness. So let's power this up and let's start it heating. So I'm going to do this gradually. So I want to get a lot of heat into the area, and I want to see if I can actually get this hot enough to solder without using the hot air. Otherwise I'll put the hot air onto a low temperature and come it from the top. So I'll pause the video. It's going to have to get up to about 200 or so. It is leaded solder, so not as hot as lead free, which is about 230. I think it's about 180 it melts, you know, without looking it up. I don't need to remember it, so I don't remember it. So let me warm this up and then I'll come back when it's getting to a higher temperature. Okay, so it seems to have settled to about that temperature. So what I'm going to do is now I'm going to turn this up to full. I'll get the hot air ready. I'm going to try the hot air to low, sort of 50% air rate. And it seems that my preheater just cannot get it any hotter than that. That's a shame. I was hoping I might be able to solder this without using any hot air, but that appears not to be the case. So let's see if I can actually maybe warm around the area a bit rather than directly on the chip. Let's see if I can increase this a bit. Otherwise we just have to use the hot air. So I'm not actually on the chip itself at the moment, I'm just trying to increase the temperature of the general area. It's obviously not hot enough yet. Okay, let's bring some hot air in over the chip, but from a bit of a distance. And I'm hoping we might see the solder liquidise effectively in this to solder. I'll just take away some. You see, as soon as I moved away, the thermocouple says it's not hot enough. I don't really see anything happening yet, and I don't think it's hot enough. That chip doesn't really look like it's doing anything, yeah. Ah, do we see the solder melting a little bit? Or is that just flux bubbling? Just pushed away. Yeah, that seems to be like it's getting towards the temperature, so let's just get some hot heat onto this now. I've got quite a high temperature, so I've moved it away, it's dropping quite rapidly. Yeah, so I'm still not totally convinced I've actually got enough heat in to do it. Okay, let's give it one blast on the top of it. Yeah. Up the air a little bit. On about 80. And hopefully this is partly soldered down now, yeah. Okay. I'm sure I must have got enough heat into that now to solder it. So let's turn the heater off. I've just put it onto the blower and let it blow. And now let's see if it's actually stuck down to the board. Okay, let's let it cool down. Okay, so I mean the chip is definitely soldered down. It's not going anywhere. It's fixed to the board for certain. It doesn't look like brilliantly soldered around the edges to me, but I had a look. So this is effectively the list I made. So if I just make the window a bit bigger, you'll be able to see it. Yeah. So I took readings on the PCB on all the 24 pins on ohms range and on diode mode. Yeah, and you can see that some pins read on diode mode anyway. 22 is 0, and that is the ground pin I checked. There's a couple of reading 59.2, this one and this one, and those are actually the phase, so those actually connect to VRAM. And there's another one, this 60.7, that also connects to VRAM as well, if you look at the data sheet. So those looked okay. So you'll notice on the chip itself there are some pins like this one, pin 8, which reads on the diode range, which also reads on the board as well. But there are some that don't. If I just have a quick look down the list, like there was like this one here, for instance, doesn't read anything on the board, but when I tried just on the chip, it read on diode mode. Yeah, and there's a couple of others. So I've just had a quick poke around this chip, and all the pins that effectively read something on diode mode on the chip are now reading something on diode mode on the board. So you would suggest that that means it's probably soldered. So I think what we best do with this now is we'll leave the MOSFETs off, so there is no MOSFETs high side or low side, so no gates can float out because there aren't any gates, yeah? And I mean, admittedly, the phase pin of this connects into VRAM. I don't imagine, I mean, it could supply some current down there, I don't know. But what I want to do is have a quick look. We'll power this up, and I want to see if we've got the 5 volts now on the VCC, which is generated by this chip, and whether we've got the, well, we know we've got the enable, but it was reading 6, whether that's now reading 3.3, which it did with the original chip. So let's have a look at what we've got. Okay, unfortunately I forgot to unpause the video, but I measured the 5 volts, and I don't have 5 volts. It was just like a decreasing, you know, like a capacitor discharging type of voltage, and the same really on the enable was low, about 1. So what I've done is I've gone around the chip again, just with my soldering iron, some flux and some solder, and just because I wasn't quite happy with the way those solder joints looked. So if we have a look now, I can just get us ready to power up. I think all the power's on. Yeah, that's ready to go. So let's find the chip again under the microscope. There it is. So this is where we should have the 5 volts, which is generated by the chip itself. And I better just put the meter in volts range where you can see it. So there's the meter. So we can have a look now. So this is your 5 volts. We should have 5 volts on here. And yes, we do have 5 volts, which makes me think then that on this little via here we'll have 3.3, yeah, 3.4. Okay, so we've got those now. So the 5 volts is working okay, and the enable's correct now. So let's have a look on the gates of the MOSFET. So this is one of them. So pin 1 is one of the gates, and is reading 46.7 kiloohms. And then on pin 8, I've got about 0.685 of a meg, so 680 kiloohms roughly, yeah, on 1 and 8. And on this one, it's the other way up. So this is pin 1, 46 kiloohms, and this is pin 8. And this is the one that blew before, 0.69 of a meg, about 0.7. So basically now they're reading about the same on both, which makes me suspect that this chip is probably soldered down properly. I certainly don't have a floating gate anywhere, so I think it's safe now to put the dual MOSFETs on, and let's have a look to see if this will now power up. I fitted the replacement MOSFET, so I'll just show you the diagram. Actually, we can check these out. So you can see that one end is 3 drains and a gate. Then this pad underneath is actually connected to those together. Yeah. The wide pad, this is the junction of the drain and source, and then the other end of the source is another gate. Excuse me. So we can look at this one. Now we know pin 1 is the gate and pin 8 is the other gate. Okay. So we can check the resistance of these to ground. Let's find the ground. So this one's reading 47k, which is how we read it without the thing in circuit. And the other gate was reading higher, yeah, 0.72 of a meg, okay? And then we can check on this one. So this one should be 47k, and the other side should be about 0.7 of a meg. Yeah, and it is. So they're reading the same, so we don't have a floating gate. So under here now, we can just check these. So this will be one of the 12 volt inputs, and this will be the other 12 volt input coming here. So if we go from here, and I go to 12 volts, which I think could be on the PCIe. Yeah, it doesn't go to PCIe. It must go to one of the 12-way connectors. Yeah, okay. So that goes 12 to 12 volts on the connector here. Okay, and the other one, which is 12 volts, on this side. I think that goes to the PCIe. Yeah, so that effectively goes to 12 volts down on the end of here, yeah? Down here. So that's the two 12 volts coming in. Now, the outer ends of these will be the grounds, so we can just go onto a ground again. Ground connection, okay. So this should be ground here. Yeah. And this should be ground here. Get a connection on it. Yeah, okay. And then the coil should attach to the big pad which is underneath here. And it connects to that one. And the other coil connects to this one, which I think is this. Yeah. And from these points to ground, which is the coils, if we just go to ground, we should read the resistance of the RAM. Yeah, at 55 ohms, okay. And the same on the other one. Sorry, it's this one. It's up the upside down, yeah. About 55 ohms. So there's no shorts. There's no shorts to 12 volts from RAM. There's no shorts to to ground. So we can power this up now. And let's have a look to see if this actually now works and if we get any VRAM. I've taken as many precautions as I can with this then. I mean, bear in mind, this is not a particularly expensive graphics card, but some of them are. So, you know, it really pays you to effectively play safe. So I'm on VRAM. I'm ready to go. I mean, last time the MOSFET just went short circuit and the PC just shut down. So let's see what happens to it now. Well, it doesn't shut down, but I don't have any VRAM still, which is a bit surprising. I honestly thought I would have that. No, I don't have any VRAM. I don't have any short circuit MOSFETs anymore. I think I'll be sure of that. Let's just go into diode range, see if it's shorts. Well, I'll put it on ohms range actually. So MOSFETs to ground, the 12 volts are on this side of them. No, no short there anymore. No short there anymore. Okay, so at least we got to that point. All the resistances look okay. So I think the next thing with this is going to be to get an oscilloscope. And let's have a look to see. Well, we can check the enable with the meter. We can check this is enabled first. We can check the 5 volts again with it on. We can check the 12 volts. And if they're all present, then I think we should get the scope. And let's see if it's actually driving any signal into these MOSFETs. So I'll just zoom the camera down a little bit more so we can see. Get into focus, there we go. Let's just see if we can get into the bit. Yeah, we've got it. Okay, so let's see. This is the enable pin, back onto volts range. This is the enable pin, should be like 3.3. Oops, power supply, I think I've switched it off actually. Switch power supply on. So that's got enable. 5 volts, it's got 12 volts, it's got, and yet there's no, just check it again, be sure. Yeah, no, there's definitely no VRAM on it. That's interesting. Okay, let's have a look to see if we can see whether or not this chip is actually driving the gates of these MOSFETs. I'll get the oscilloscope ready. I've got the oscilloscope ready then. So let's get onto these chips. So let's have a look at the gate of these here. So this is one of the gates. Make sure I just get a connection to it. Yeah, okay. I need to ground the oscilloscope, guys. You can see that. That's why I'm getting like that happening. Yeah. So one of the gates is here. In fact, actually, it may well be easy just to check on the chip because we know where the test points are. So this is one of the gate drives here. Let's have a look at this. See, we'll start it up and does anything happen? Power on. Okay. No, there's no drive. You can see that there's no pulses coming out. Yeah. This one, I believe, is one of the other gates here. Switch it off. Switch it on. No, this VRM control just isn't sending any, pulse width modulation to the Gates, this is one of the other ones. No, nothing there. And the last one, I just have to find my bit of paper. I'm pretty sure it's here. Nothing. I don't think it was that one. Yeah, that's a sort of voltage on it. I'm pretty sure it was this one actually. Well, that's interesting because it's like we've got no drive getting to the MOSFETs, but we know we've got the voltage on here. We know we've got the enable on here. So you would think this should be oscillating. Maybe there's some other reason why. I mean, we're kind of back where we were in the first place before I changed the chip, where it didn't oscillate. So I need to have a look at the data sheet and see if I can figure out anything else that's around this that actually could stop it driving the MOSFETs. Let's have a look then to see if we can figure out why this isn't actually working. Okay. This is the data sheet then for the actual 8811A, that's our chip. And we can see the layout. And this describes a pin. So I'm going to have a look around the pins of this chip to see if I can actually figure out if there's any reason I can see that it's not working. I mean, we know it's got power. We know it's got enable. So it should work. So let's just go through the pins in turn. So first one, boot 1, that's saying this pin provides power for the high side MOSFET driver. So I'm guessing there should be some voltage on pin 1. So that'll be the first one we can actually have a look at to see if we've got something there. I'll just power the board up. That's on. And I've looked down the microscope, I should be able to find that. So yeah, it's bleeping because it didn't find the card. So let me just find where I am. Okay. So pin 1 is here. And that has 11.6 volts on. So that's got power, according to the data sheet. Pin 3 we know is working. Pin 4, power saving interface. When the voltage is below 0.8, the device operates. Oh, no, yeah. This selects single phase or dual phase mode. So it doesn't really seem to matter as long as you've got some voltage on here. I mean, even if it's below 8, this is suggesting this would work in single phase. But let's have a quick look on pin 4 anyway, just out of interest to see what we have on this pin. So once again, just find where I am. 1, 2, 3. Pin 4 is here. So that has 2.9 volts on. So that kind of puts it in this range here, 2.45 to 5.5. So that's what we'd expect. Next one then, and I'll just make sure this. Yeah, the GPU's just not really getting warm because there's no power, only PEX power on it. A little pad on there. VID, programming output voltage control input. Well, I don't think there's anything we can really check on there. I suspect it's like serial data from the GPU telling it what voltage it wants. Ref adjust, reference adjustment voltage 6. I'd expect this and ref in to be the voltage that the VRAM wants, which is 1.5. So let's have a look on there. I'm guessing there should be a reference. Let me have a look. So pin 6 is this one. And that has, yeah, 1.5 is I expected. And I'm expecting pin 7 should be the same. Well, yeah, it's very close, isn't it? It's very close. So I know there's a problem there. Pin 8, it says it's a reference voltage, and it says it's a high precision voltage reference, 2 volts. So I think we can say for certain there should be 2 volts on this pin, pin 8. So let's have a look at that one. So let's just find out where I am. Pin 7, pin 8. 1.97. Okay, that's good enough. Next one, TON, on-time switching frequency adjustment. Okay, what's that one? What's that one? Pin 9. So 7, 8, 9 is on the sort of via. That's 0.14. I don't really know what should be on this. I'm just, oh, that's strange. That's moving around. That doesn't look. Switch it off. Oh, that's interesting. When I switch it on, it goes to negative. That suggests that pin is actually open circuit. When I see a negative voltage like that, and 8 was floating around after that. That looks like that pin's actually open circuit. Let's have a look, see what that is. On-time switching frequency. This sounds like where you would normally have a resistor and a capacitor that sets the frequency for the oscillator. And I think a problem here would certainly stop it working. Let's have a look. So, is there an application? Oh, this will do. So we've got power. Oh, this is it. Pin 9. Oh, that's interesting. Look, this shows this comes from Vn. And Vn is the 12 volts. It's there, Vn on the top of the MOSFETs, yeah? So 12 volts coming in through a 2.2 ohm resistor, through a 500k resistor to here. So you would expect to be a positive voltage on that, not just like floating around. It certainly wouldn't be floating around. I mean, assuming, unless this capacitor's gone short or noisy maybe. Let's have a look. I'll measure the resistance from here to 12 volts and we should see 500k plus 2.2. Yeah, about 500k. And to ground it should read open circuit because this capacitor should just, to emitter should read open circuit. So let's have a look to see what we've got. So it's switched off. Go to resistance. So it was pin 9. This one. And it reads open circuit to ground. That's what I would expect. Okay. I'll just get my meter probe onto 12 volts. So I'll just find, I'll have to take this off the adapter to get to the 12 volts connection. Okay. So I'm on 12 volts on the PCIe. Let me get onto here again. On this little device. Sorry, I've moved these, that's why it's out of focus. Let me just, hopefully that's back in focus for you guys. So, from this little wire here, 7 pin 9 to 12 volts. It's not going to the PCIe. And it's not going to the 12 volts on the 8-way connectors either. So you can see the meter, I mean you can't quite see where I'm probing. I'm just checking from there to 12 volts on both the 6 and the 8-way and the PCIe. That's open circuit. That's wrong. That is wrong. Right, let's see if we just figure out this a little bit further. I've got the schematic again for the Gigabyte GTX1080 Ti. I mean, ours is a Zotac. It's not the same, but it's similar. It uses the same chip here to power the VRM for the VRAM. And this is pin 9. It's hard to see, it's underneath the marking for the component here, but this is pin 9. And here we have a 383k, so it's not 500k like the example circuit, but it's a high value. 383k resistor is a 1%, so it's a close tolerance. And that resistor goes to this point. Okay. From this point, it goes through the 2.2 ohm resistor to 12 volts. Yeah, that's what we could see off that example circuit. And then from here, there's a capacitor to ground, which is a 0.1 microfarad. And it also shows a resistor to ground as well, which is 47k. So with my meter probe here reading to 12 volts, I would expect to find, well, assume it's the same as this, I'd expect to read from here to here about 383k, and I'm reading open circuit. And then from here to here, if I was as this resistor as well, I'd expect to read 384 plus 4.7, there's another 50 roughly, 390, 440, 430k to ground. And it's open circuit, so that's like, either our circuit isn't the same as this, or this resistor is open circuit because it doesn't read either way. So what I'm going to do is, I've got the Gigabyte board that matches this schematic. So that's the one I took the donor chip off. But I can measure from this pin to 12 volts and ground and see, I should on that one see these resistances because that's what it's showing me on here. So let's have a look at that and let's see if we can actually see those resistances. This is the donor board then. So this is where I removed the chip from this one. So we're interested in pin 9. this is pin 1. You can see there's like a little square thing there. See in the silk printing, and then there's like a little triangle, a little diagonal there. So this is pin 1 down to 6, 7, 8, 9. So pin 9 is in the centre of here, and I'll have to use the microscope so I can actually get on it. So I need my stereo vision. Yeah. So we're on there, and I'm going to measure first of all to ground, and I'm expecting it might be like 47k. And that's actually, let me just so I can see the range myself. It's actually, we'd actually reached about 390. Oh no, it's not 47, sorry. We were going to say 383 plus 47, which, yeah, so it's about, you know, sort of what you'd expect, about 400. And then to, just trying the PCIe, yeah, and there to 12 volts on the PCIe, we see 384k, which is exactly what you'd expect to see on that chip. Now, our board, if we just get us under the microscope, okay, here's our board. So again, on this one, pin 9 is actually on a little via here, yeah. So from here, again, I want to go to the 12 volt on the PCIe, and there's nothing. And I checked earlier on the other 12 volts in case it goes on this board to the 6 or 8 way, and it doesn't, there's nothing. And to ground, there's nothing. So that suggests, as I said before, that 383k, if it is 383k on our board, to match the other one, and not 500. But I'm guessing it probably is likely to be matching that one. It's open circuit. So what I need to do now is figure out where that resistor is. So it goes through a via here, it goes through the board. I don't think it goes to any of these other components around here. No, I don't think that. I think it's going to the other side. So what I need to do now is trace that to have a look to see where it goes. I'll just, I might even tag a little bit of wire on this side. Oh no, I can see where it does go. One moment, let me just check. Does it go down here? No, it doesn't. There's like a track thing coming up here that kind of like doesn't go anywhere. It doesn't join onto that. I bet that's a ground acting like a shield, maybe, because I suspect the voltage on this is very sensitive because it sets the frequency of the oscillator basically. And actually, if you look at that data sheet a little bit further, it does actually tell you exactly what this does, and it does set the frequency. Yeah, I'm on ground. That is ground. That thing is going up there. It doesn't join to there. I think it's just acting like a ground plane, like a shield. Yeah. Okay, so let's have a look so we can figure out where this goes on the other side of the board. I can see where that goes to, and I'll show you how to see it on the other side of the board as well. You see there's like a via here, and then sort of coming like diagonally this way. There's two more there, yeah? And I can see, you see that pattern, but like a right angle triangle, if you like, with this at the acute end of it, which I'm sure it's got a name in geometry, but there you go. And all that is kind of like just this side of this hole here on the edge of the board. So we flick the board over, that's the hole. So it's up here somewhere, and we can see it. Right, we can see the pattern. It's kind of like a mirror image. That's effectively the triangle, yeah. And this is the apex, is that the name for it? The sharp end of a triangle. And if you look here, there's something very interesting, because this is a component broken off the board. You see it there? That is something broken off the board. And this, you'd assume, is where, if it's the same as the other one, it might even be that this is the 12 volts. Yeah, just focus on that properly. It's looking to me, I haven't measured this, but let's measure it. That this could be 12 volts. This could be our 380k, 384k resistor. I won't worry about the 2 ohm resistor if there's 12 volts on here. And I'm wondering if one of these, if this is ground, then one of these is supposed to be that capacitor and one's supposed to be that 47k resistor, and for some reason they've been taken off the board. This is broken though. This is definitely broken, 100%. You can see that. So let's have a look from. Let me just get to the microscope. This makes it easier. You can see we want resistance. We're on resistance range. So let's have a look from here. yeah, and see if this is 12 volts. Okay, so from here to 12 volts. Yes, 12 volts from the PCIe goes to there, yeah, from the PCIe connector. I'm just going to interrupt the video here to point out a mistake I've just made, because I know a lot of you guys got very sharp eyes and you'll be all over the comments with this one, yeah. So, this point here, this goes to pin 9 of the VRM controller, the RT8811. And this here is where we would have the 384k resistor, this then being 12 volts, okay. But these 2 points here cannot be the 47k resistor and the 0.1 microfarad capacitor shown on the gigabyte schematic. And the obvious reason for that is that they connected to the wrong end of the 384k resistor according to the schematic. So they cannot be here. So when I mentioned again a little while about these, whether they were fitted or not, if they were, they certainly weren't the components that we thought they were. Okay, let's continue. So that's definitely the 12 volts on that point. So this would be our 384k, if that's what it is. What's here? So is this here ground? So it goes to the end of this, which is the emitter of a transistor, which is almost certainly going to be ground. It's got to be a ground point somewhere. That's ground. So now is the question. We can definitely put in here the 383k resistor, if that's right. And it's whether or not do we fit the capacitor in the 47. It doesn't look to me. I'm interested in what it looks like to you. It doesn't look to me like these other components were ever there. Yeah, these two. But this has definitely been broken off. Yeah, I think we can confirm it. Just really, yeah, there you go. In fact, I think you can even see the end of the component that's come off it now. So we're going to have to put a resistor in here and see if it works. I would really love to have another one of these cards to compare it with, because if I get it wrong at the wrong frequency, I might blow the MOSFETs again. But then we have to take we have to take some judgment here, yeah. So I'm going to take the judgment that according to the typical application, well then there should be 500k and there shouldn't be the other one. Oh, what do I stick in there? Let me just think. Well guys, as much as I'd like to get this fixed today, I think I'm going to chicken out. And say chicken out, I mean, I think I'm going to find out if somebody's got one of these who can measure this resistor and just check those other two components, whether they fitted or not. If we just look at that gigabyte one again, I'll just explain why I came to that decision. So this is the circuit. So this has a 383k resistor and its tolerance is 1%. So it's a close tolerance, yeah. It has a 2.2 ohm and that's 1% as well. This resistor is the one that effectively that looks like ours I never had fitted, and the same as the capacitor. And obviously these are not high tolerance. There's no tolerance even mentioned on that. Probably 5%, and this is 10%. Now you might think you've got 12 volts coming in here, and then this is going to ground. So you think you were correct. This resistor and this resistor form a voltage divider, but this 47k is so large compared to that 2.2 that the voltage here on the divider is almost 12 volts regardless of whether that was fitted or whether it isn't fitted. It wouldn't really have any appreciable effect on the voltage here. Yeah, it's minuscule, the difference it makes. But this is important, and I think because we can't guarantee our circuit is the same as the other one, although it's probably very similar. If I put the wrong value resistor in here, if I put a higher value in, it actually decreases the frequency of the oscillator. I can actually show you that if I just find the data sheet again. Yeah, this is the data sheet. So this shows it here. It shows the calculation for T on, time on, yeah. and it depends on the resistor, as we know, okay, and the frequency depends on the resistor, and it shows you here. So from the resistor from about 250k is about 750 kilohertz. So yeah, 750 kilohertz. By the time you get to about 500, the frequency is about 300 kilohertz. So 380 is going to give you about 400. So the difference between the sort of 380 and 500 is about 100 kilohertz. Now, if the frequency is too low, or maybe just plain wrong, either the type of FETs maybe just can't switch on and off fast enough, or possibly if they switch on for too long, what would happen is the inductor coils would saturate and it would blow the FETs. So basically, these, if the frequency is too low, each of these is on for too long. By being on for too long, it fully magnetizes the coil, and that can blow the FETs. So that's one reason why I think I'm going to wait for some information on this one. The other reason, it basically comes down to cost. Obviously, I want to try to recoup my expense on these cards, although the last one I fixed probably covered it, actually. Just fixing 1 out of the 10. But you can see that on eBay, this is sold listings. So 12th of January, that's a TI. By the way, this is not a TI, this is the non-TI. But 11th of January, one sold there in auction at 101 working. These are parts only. 78 parts only. Parts only. 185 working. Yeah, 102. So this graphics card is like about £100 worth. And for the sake of trying to get this repair completed on part 2, I think it's worth finding out what the value of that resistor is. And the third reason is because if I publish this now, hopefully somebody can tell me exactly what to fit in there. Yeah. So, okay, guys. Almost a success. And you can see with this one, really, it's down to the previous engineer who just didn't do the job properly. I mean, if this works now, once I get the right resistor, and I'm very confident it will work, actually, because that fault would stop this from oscillating. That would definitely stop it from working. So somebody's obviously, this has been reworked before, so somebody's looked at this, okay, and they've traced the problem down to this not driving the MOSFETs, and they've obviously figured out there's no shorts because they haven't changed the MOSFETs, and they were okay. So they've either changed that or they've reflowed that. And at that point, it didn't work, so they've given up. But from what you can see, I've just shown you guys, I've not done anything clever here. All I've done is taken the data sheet. Once I've figured out that this isn't working and it's enabled, it's got power, I've taken that data sheet and started going around every pin on it to see if it has the voltage you'd expect, and it didn't. And that's no genius, is it? That's just, you know, look at this data sheet and just measure them, yeah? So, there you go. I hope that's taught you something, guys. Sorry it's not fixed today. I'd love to stick a resistor in there and just see if it works, but because of the possibility of some failure here, and I might send more 12 volts into the RAM, I'm sure you can appreciate why I'm not going to do that. Hopefully next week, or as soon as somebody gives me the value of that resistor, we will definitely have this with the component in, and see if those other two, by the way, are missing or were never fitted, and then yeah, let's see how it goes. Well, about a week's gone by since I made this video, and I asked on a couple of places. I've asked on Tech Cemetery on their Discord server, and I've asked on Bad Caps in the GPU repair section, but nobody seems able to tell me what the value of this resistor should be. And because it's such a critical component, I mean, it's 1% tolerance, it's obviously critical. I decided the only really way to find out was to get another card. So I went on eBay at the weekend, and I'll just show you what I have. Yep, so I actually won this one in auction, so it's £54.90. This is a Zotac GTX1070 Ti, but looking at the image, this is the same board as mine, and I can even see where that resistor is basically. So I'm confident really that once I get hold of this one, I'll be able to actually just, you know, measure the resistor on it and fix mine. And with a bit of luck, I may be able to fix that one as well. So it seemed like the best way to do it. I couldn't find any other really realistic way to figure out what this component was. So that's coming into the UK. It might not arrive here for a while because my wife is going back to the UK around Mother's Day, which is in March. And I already have 5 other graphics cards sitting in the UK waiting to come over here, and I think now it's probably worth just waiting. When she goes over, she can bring them all back with her. Okay guys, so not fixed but diagnosed for sure, yeah, and I think we can say with a high degree of confidence that we'll have this one fixed, that it was a resistor again, the same as the last one which I repaired. So once again, spares or repair graphics cards from eBay, and it looks like it's not, you know, a burnt out GPU or video RAM. Okay guys, I'll let you know if I will make a video when the other card arrives, and at the same time we'll try and fix this as well, and look forward to that video. Okay guys, see you soon now. Adios amigos.